Hopefully there's like, I think it's like a sheet tab, it's gonna be like a crap, you know?
Alrighty, so reminder that the SR metric is ds squared is c squared dt squared, and then if we're in Cartesian spatial coordinates, minus dx squared minus dy squared minus dz squared, and again those are like dx times dx, not the differential of x squared there, not 2x dx, that means dx times dx. And remember that it is unchanged under Lorentz transformations, as you will joyfully show in the first homework problem that I've assigned. You'll explicitly show that if you transform to the prime frame, then it has exactly the same value in both frames, and it has exactly the same expression in both frames as well, namely it'll be dt prime squared minus dx prime squared minus dy prime squared minus dz prime squared. So it's unchanged under the Lorentz transformations. Analogously to how the ordinary distance, this is kind of like the space-time distance ds squared. It's not literally a distance, but we call it the squared interval. Analogously to how the ordinary distance, which is just, call that dl squared, which would be dx squared plus dy squared plus dz squared, is unchanged by a coordinate rotation. Just rotating the axes doesn't change dl squared, doesn't change the distance between points. So Lorentz transformations play the same role in special relativity that rotations do in Euclidean geometry. They play an analogous role. They're a general class of transformations that don't change what we think of as like the distance between points. In fact, a rotation is a special form of a Lorentz transformation. The rotation group is a subset of the Lorentz transformations where they're just not moving. The two frames are not moving with respect to one another. You've just rotated the coordinates. And then I want to remind you that if ds squared is greater than 0, because notice that unlike the usual distance between points squared, which has to be positive, this has the funny property that ds squared can be negative because it's got a time piece minus the sum of the squares of the space pieces. And so it could be that the space pieces are bigger than the time piece put together, and you could get a negative value for ds squared. But if ds squared is greater than 0, then d tau equals square root of ds squared divided by c is the proper time interval between two events. Or in other words, it's the time elapsed on a clock in a frame that experiences both events. It's a time elapsed on a clock that experiences both events. I'll even say that travels between the two events and experiences them at its location. So if Fred stays on Earth while Sally travels from Earth to Zorkon, consider Sally departing Earth and Sally arriving at Zorkon. What's the proper time interval? Whose clock tells you the proper time interval between Sally launching from Earth and arriving on Zorkon? Yes? Sally's clock, right? Sally's clock is the one that travels from her launch to her arrival on Zorkon. So Sally's clock reads off the proper time interval between those two events. Then it's Sally's clock. That reads off the proper time interval between her departure from Earth and her arrival at Zorkon. She's the one who reads off that proper time interval. Call Sally's rocket frame. Let's say she's frame S prime. Her frame is S prime, Earth's frame is S. What are delta X, delta Y, and delta Z prime, I should say prime, because it's the prime frame. What are delta X prime, delta Y prime, and delta Z prime in frame S prime, the rocket prime? Between her launch and arrival. What are delta X prime, delta Y prime, and delta Z prime for Sally? What does Sally say the change in her X coordinate is between when she launched at Earth and arrived on Zorkon? Yes?
She would say that there was no change and that those things moved faster.
Yeah, she'll say that, well, her launch and her arrival both happened at the same location, namely her location, right? If she puts herself at the origin of S prime, then her launch is at X prime equals 0, Y prime equals 0, Z prime equals 0, and her arrival at Zorkon is also at X prime equals 0, Y prime equals 0, Z prime equals 0. And so Sally says all of these things are 0. they're all 0. Since launch and arrival both occur at her location. They both occur at her location. So now I'm going to, instead of saying ds and dx and dy and dz and dt, which I could, I'm going to go ahead and call them delta x, delta y, delta z, etc., just to emphasize they don't have to be small here. And that's what I do in the homework problem too. In other words, in the flat metric of special relativity, no gravities around, the points don't really need to be close to one another. They can be large separations and still everything applies. In curved spacetime, the metric only tells you the distance between spacetime events that are so to speak right next to one another, little differential differences in the coordinates. But in flat spacetime, the distances you've traveled, etc., can be as big as you like. So she says that delta s squared is, well, in anybody's coordinates, it has the form c squared times the time difference squared, but she's in the prime frame, at rest in the prime frame, so she says it's delta t prime squared minus delta x prime squared minus delta y prime squared minus delta z prime squared. But what are delta x prime, delta y prime, and delta z prime, says Sally, between those events? 0, 0, 0. 0, 0, 0. So delta s squared is c squared times delta t prime squared. So in other words, the time ticked off on her clock is delta t prime equals delta s divided by c. Or if I want, I could say it's the square root of delta s squared divided by c. So delta s divided by c is the time ticked off on Sally's clock, and we call a proper time interval like that between two events delta tau. Tau represents the proper time interval. Tau represents proper time. So along the world line of a clock, it's directly reading off the time on its own clock, and tau along its world line is proper time along its world line, and any difference in its readings is delta tau. Questions at this point? So you'll be more quantitative in the homework, but, and it's not going to be Fred and Sally in the homework. I don't explicitly mention the twin paradox, but it's definitely the idea here. Time dilation comes out of all of this because Fred says delta s squared is c squared. Fred, at rest in S, at rest in Earth frame S, says delta s squared is c squared delta t squared minus delta x squared minus delta y squared minus delta z squared. What's all this according to Fred? What is minus delta x squared minus delta y squared minus delta z squared? Or put another way, what is minus the quantity delta x squared delta plus delta y squared plus delta z squared for Fred between Sally's departure and her arrival. What's that? Yeah, it's the distance squared between Earth and Zorkon, according to Fred. It's the distance between those two events. The distance squared from Earth to Zorkon, from Earth to Zorkon, so Fred does that calculation. And he gets a certain number. How does that value compare to the number that Sally gets doing the same calculation in her coordinates? So delta S squared is the squared interval between this pair of events. Between any pair of events in space-time, we have the squared interval between them. And we had this fundamental postulate of relativity from which everything else essentially follows, along with an assertion that the laws of physics are the same as seen in all inertial reference frames. What do we say about the squared interval between any two events? Does it change from one frame to another? No, it's invariant. Everybody agrees on the squared interval between any pair of events in space-time. It serves as sort of the distance between them, the space-time distance between them, if you will. Just like if I've got 2 points on the board, I could have, no matter what coordinate system I have on the board, no matter what Cartesian coordinate system, the distance between them is the distance between them. So it doesn't matter whether I use x, y, or some rotated coordinates x prime, y prime. If I add up the sum of the squares of the coordinate differences, that's the square of the distance between the points. And analogously, this happens in space-time too. Any pair of events, delta S squared, is the same no matter which frame of reference you use to calculate delta S squared. Did you have a question? I just answered it, yeah. No matter what frame of reference I use, everybody gets the same value for delta S squared. And again, in the homework, we'll explicitly show Lorentz transformations preserve delta S squared, although the logic is we postulate that delta S squared is agreed on by everybody, and that constrains how Lorentz transformations have to work. In other words, Lorentz transformations are the coordinate transformations that preserve delta S squared from one frame to another. Do you now have another question? Yeah. So unfortunately, it's very standard to call frames with capital S. So yeah, capital S, and this is little s for the space-time interval squared. Unfortunately, that's a very standard. Who came up with that? Not me, but I'm using it because it's so common.
That shows instead of the fancy like charm and
This is fancy what?
the charm, strange charm.
Oh yeah, the same people that said top and bottom instead of truth and beauty.
Yeah.
Right, I mean, come on, right? Okay, I can see up and down. Okay, let's go. That's mundane. Those are the mundane quarks. So you go to the next generation, strange and charm. Oh, wow, cool. Okay, let's go to the next generation after that. Should we do top and bottom or truth and beauty? Not top and bottom, but that's what they picked. Okay, anyway. So, okay. But this is the same thing as c squared delta t prime squared, because that's what Sally got for it, and everybody gets the same thing, right? So, which one's bigger, delta t or delta t prime? Which one's bigger? Delta t has to be bigger because c squared delta t squared minus delta L squared is the same thing as c squared delta t prime squared. So delta t must be greater than delta t prime, t prime. Or in other words, than the proper time interval. Fred says it takes longer in his frame for Sally to get to Zorkon than she says in her frame. And in the homework, and it's not a huge leap from this, in the homework you'll show that it's exactly the time dilation formula that comes out of this. It's the usual time dilation formula. Fred says it takes longer in his frame for Sally to arrive at Zorkon than she says it does in her frame. Time dilation. In the homework, you'll show that delta t prime is equal to, how's it work? Do you remember? By what factor is delta t prime going to be smaller than delta t? By what factor does the moving clock tick slow? Hint, it involves that funny gamma thingy. Oh my God, you just haven't burned this into your brain. It's this. 1 over gamma times delta t, where gamma, do I have, now I'm probably putting this back. Let's see, got to think about it here. Gamma's bigger than, yeah, gamma's bigger than 1. So what is gamma again? Yeah, 1 over the square root of 1 minus v squared over c squared. 1 minus v squared over c squared, right? So this is always going to be bigger than 1 because square root of 1 minus v squared over c squared is smaller than 1, and 1 over something smaller than 1 is bigger than 1. So delta t prime is smaller than delta t because I'm dividing by something that's bigger than 1. And so I'm sure you did plenty of homeworks involving, well, let's see if you're going at 0.6 the speed of light, right? Then how does this work out, et cetera, et cetera. For the time dilation factor, you'll show, it's actually not too hard, that invariance of the interval gives you the time dilation formula. It implies the usual time dilation formula. What questions do you have? Including, what? See, people are still writing, so I should pause, let you all catch up here. Can I erase this stuff on the side? Okay. Yes. Did I mess up?
No. Does it go the distance squared from Earth to Zorkon?
Yeah.
And then Fred says it takes longer.
What's that?
Fred says it takes longer.
Fred says it takes longer than Sally does. Yeah, now this is the distance squared from Earth to Zorkon in the Earth frame. right? Remember that length contraction says, well, Sally says that the distance is shrunk, right? Because to her, she's sitting there and they're flying past, and the distance between them is smaller for Sally than it is for Fred. But this is the distance squared from Earth to Zorkon in the Earth frame. What do I want to say next? Yeah. All right. Now, one thing I should add that is if ds squared is less than 0, which can happen, right? Then the interpretation of ds squared is that dl is the square root of minus ds squared. I need minus because ds squared itself is less than 0, so I don't want to take the square root of something that's negative, minus ds squared would be positive, is the proper distance between two events. It's the proper distance between the two events. Or in other words, the distance between the events in a frame in which they are simultaneous. Because in such a frame, suppose you're in a frame where the two events are simultaneous. What's delta t according to your frame if the two events are simultaneous? By definition, what's delta t between those two events? It's 0, right? They happen at the same time. So in that frame, and again, I'll let it be delta s here. I can make it ds still if I wanted, but delta s squared is equal to minus delta x squared minus delta y squared minus delta z squared equals minus delta L squared. Delta S squared is minus the distance squared between the two events in that frame, so we call that the proper distance, the distance measured in that frame, the frame in which they're simultaneous. In other frames, the events aren't simultaneous anymore, but we can still call this the proper distance between them, and you can use this to derive length contraction. One can use this to derive length contraction as seen in other frames. Not going to do it, but you could. So now let's write the Minkowski metric, the metric of flat space-time in spherical polar coordinates. So, in spherical polar coordinates, the Minkowski metric of flat space-time will be ds squared equals c squared dt squared, and then it's always minus minus the distance squared between the points. So do you remember in spherical coordinates we said that the distance between 2 points, do you remember what the pieces are in that case? What's the dr piece look like? Do you remember? What's that? So I'm asking what's dl squared, the distance between 2 points in spherical coordinates, as opposed to Cartesian coordinates where it's just dx squared plus dy squared plus dz squared. In spherical coordinates, it's got sine theta in it, it's got theta, phi, and r in it, it's got dr, d theta, and d phi in it. How do they all come in? This is worth just burning into your brain, it really is, because it just comes up over and over again, not just here, but in all kinds of contexts like E and M and so forth. So that's in there. It's dr squared for the radial piece. Okay, and then there is a piece that involves d phi, yes? Squared, yep, so r squared d phi squared. And then the fancy one that's got the sine theta in it is where of course every is a syllable. So we've got So now that's two sets. So it's r squared sine theta sine squared theta Actually, sorry, I screwed this up. This is r squared d theta squared, I meant to say. Oops, bad me. Plus r squared sine squared theta. Can it just be there by itself like that? Squared, yeah. dr squared plus r squared d theta squared plus r squared sine squared theta. Burn that into your brain and be able to, like, you know, just because it's the coordinate differences just squared, right? So in other words, if I'm the origin here and my arm is r, I can go 3 displacements that are perpendicular to one another in spherical coordinates. There's a dr is the displacement radially. R d theta is the displacement in the theta direction, and r sine theta d phi is the displacement in the phi direction. And add up the sum of the squares of those 3 perpendicular displacements. That's the square of the distance between the points. So in spherical coordinates, the Minkowski metric, instead of minus dx squared minus dy squared minus dz squared, it's minus dr squared minus r squared d theta squared minus r squared sine squared theta d phi squared. This is the flat space-time metric written in spherical coordinates. And the Schwarzschild metric looks just like this, except there's decorations on 2 of the pieces. The Schwarzschild metric is this decorated to represent the curvature of space-time. So, in this case, we can find Cartesian coordinates to cover all of space-time. Right, we could write ds squared as c squared dt squared minus dx squared minus dy squared minus dz squared. But according to general relativity, always salute general relativity. According to general relativity, right, as we've said multiple times, gravity is curvature of space-time. Gravity is curvature of space-time. Due to the presence of mass energy. I say mass energy because in Newtonian gravity it's mass. But remember, in relativity, mass and energy have a certain equivalence. So they both contribute. If you heat up an iron skillet, it has more gravity because of the kinetic energy of all the vibrating atoms in it. Because of the intrinsic curvature, no coordinate system can be constructed, just doesn't exist. No coordinate system can be constructed in which the metric takes the SR form, special relativity form, everywhere. Can't do it. You just can't transform away gravity everywhere. In a non-uniform gravitational field, the best we can do is to construct a local inertial frame in free fall. We've talked about those. A local inertial frame in free fall. In such a frame, you can write the metric as the special relativity metric if you attach coordinates to that frame, but you can't cover all of space-time with them. They're only local, and they really only work at a single point, and the further away you get from that point, the further away it becomes from this being a good description. But this is that whole business of principal equivalence over a small enough region of space and a short enough interval in time. If you use coordinate system attached to a falling compartment, a freely falling compartment, fill it with clocks, fill it with meter sticks to make an XY coordinate, XYZ coordinate system, or even fill it with a contraption of meter sticks that are arranged in spherical shells to make spherical polar coordinates, do whatever you like. You can make a good approximation to special relativity holding in that frame. And this would be the metric inside that frame in spherical polar coordinates, but it only works over a small region, and the bigger the region, the further you get deviations from that form. So the local inertial frames in free fall are analogous to local Cartesian coordinates on the surface of a sphere. It's analogous to that situation. So the local inertial frame plays the role of the local Cartesian tangent plane coordinates for a sphere. I'm going to say a local inertial frame plays a role analogous to local Cartesian tangent plane coordinates for a sphere. For a small region of a sphere, or other curved manifold for that matter. Doesn't have to be a sphere. Okay, now we're approaching a super important result. Much of general relativity comes down to this result we're about to get to here. What questions do you have at this point? Wonder if I've got a globe in here. I want a globe, and if I don't, I'm going to run and get one in between periods. Do I have a globe in here? Please be a globe in here. I want a globe in here. Yes, I have a globe. And look, I have a distance marker too. Okay? So, y'all ever heard of great circles? Did you learn about great circles anywhere? Like this, the shortest distance between 2 points on Earth's surface is a great circle between them. That's what I'm referring to here. Okay? On a plane, not a, but I mean, you know, the board, right? On a plane, because planes tend to fly on great circles, but different plane. On a plane, the shortest distance between 2 points is a what? If I wanted to draw the shortest path between those 2 points, what would I draw? I would draw a straight line, yeah. Is a straight line. Is along a straight line joining them. Everybody knows that. You've known that since whatever grade. The straight line tells you the shortest distance between 2 points. So I could grab my little straight distance my distance majigger here, right? And if I want to make the shortest possible distance, I just stretch it taut between them. There it is. And any other path is going to be longer than that, right? Y'all know that. But on the curved surface of the Earth, because it's curved, you can't literally draw a straight line between any 2 points on the surface. I'm not allowed to tunnel inside. I'm constraining myself to the surface of the spherical Earth. And of course, the real Earth is a geoid. It's not perfectly spherical, blah, blah, blah. Shut up. Cue ball Earth, where it's a perfect sphere. On a sphere, the analogous thing to a straight line is what we say it's called? It's a great circle. It's a great circle. It's a great circle. Great circle, which, to be a great circle, it has to be something that could serve as an equator, as part of an equator. In other words, the plane of that arc would pass through the center of the Earth in order for it to be a great circle. A great circle needs to be part of a circle that would split the sphere into 2 equal halves, an equator, so to speak. So, in other words, if I string this along a line of longitude, have I created a great circle arc in that case? Along a line of longitude. Does that split the Earth in 2? No, if I continued it all around, it wouldn't be splitting the Earth in 2. It has to split the Earth in 2. A great circle arc has to be part of what could be an equator, right? The actual equator is a great circle, and any other circle that could serve as an equator, and now I'm ignoring the rotation of the Earth and I'm just thinking of it as a general geometric sphere, a circle that could serve as an equator. It splits the Earth in 2. The plane of that circle contains the center of the sphere. That's what you need for it to be a great circle. That's what I need. That's what I mean by that. The plane in which the circle lies passes through Earth, passes through the center of the sphere. So, for example, and this, this can surprise people, especially because on a flat maps distort the great circles. A great circle is the closest thing you can get to a straight line path between 2 points on the surface of Earth. And so, for example, not that there's any direct flights between us and Tokyo, obviously, right? But, well, it's not obvious, but there's not. If I wanted to fly straight from Columbus, which is here, to Tokyo, let's say, which is here, okay? If you look at a flat map, you'd think you'd fly over the Pacific Ocean in order to do that, but you don't. If I stretch a great circle between us and Tokyo, it looks something like this. So you fly over the Arctic. You basically don't fly over the ocean, you fly over the Arctic because your plane wants to conserve fuel. You want to fly the shortest possible distance, so you fly a great circle arc on the Earth subject to constraints like maybe Russia doesn't want you flying over their territory. I have flown over Russian territory back when we had friendlier relations with Russia, so I've seen Siberia from the air. You don't get to do that anymore because we don't have such friendly relations with Russia once again anymore. Question?
In terms of like flying, is that the same thing as a geodesic curve?
Yeah, yep. I just haven't written the magic word yet. So actually, let's make that the last thing we do before the break, okay? In local Cartesian coordinates, on a sphere, a great circle is a straight line near any point. I'll say a great circle projects to a straight line on the tangent plane and vice versa. So if I want to drive to downtown Columbus, that's not a huge arc on the Earth. And, you know, for all the world, the Great Circle from here to downtown Columbus would look an awfully lot like just a flat line on our little portion of the Earth, for example. Or better yet, when you walk to your dorm, right? If you walk a great circle to your dorm, boy, that sure would look like a straight line on Google Earth or Google Maps, right? Or Android Auto. For short distances, they're going to just look like straight lines on a flat map. But if you get a big section of the Earth where you can't ignore the curvature anymore, well, it's clearly a curved path, but it's the straightest possible path that you can pull off. A shortest possible path is a, say it, geodesic. Well, it is, but it's on a sphere. But if you're not on a sphere, if you're on a saddle, for example, it's not a great circle anymore, but in general, we say a straightest possible path is a geodesic, is what we call it. A shortest possible path is called a geodesic. On any, I'll use the fancy word manifold, doesn't have to be a sphere, is called a geodesic. And after the break, we'll talk about how the role of geodesics in curved space-time, even in flat space-time, is of all the ways you could get between two events in space-time, the world line that a free particle actually will follow, one with no forces on it, is the geodesic path, which is the one that maximizes the proper time between the two events. Because of the funny signature of the space-time metric, where it's got a positive time piece and a negative space piece, it turns out that on some level, the geodesics are longest possible paths. They're the ones that maximize the proper time between them. But we'll talk about that after the break. Okay, changed it to say on most any manifold because in general relativity, because of the weird, if you will, distance measure that can be, where you can have the distance squared being negative. It turns out in general relativity, in space-time in general, that we actually typically maximize the proper time. So continuing on, in relativity, the role of the distance between events along the world line of a particle is played by the proper time. In relativity, both special and general, just relativity in general. In relativity, the role of the distance along a world line along, I say, the world line of a particle so, right, remember that the world line is its space-time trajectory, if you will, right? So that's like a world line there of a particle in space-time. If the particle is moving at constant speed in a straight line, what's the world line look like? Then it's just a straight line between events, right? So this is a particle that's accelerating. It's changing its speed because it's the curvature of the world line says that. So imagine that the particle's carrying a clock, right? We always imagine our particles are carrying clocks. Particle clock reads tau, and it's marking off, if you will, distance along the world line. Space-time distance along the world line. The proper time interval between events is what we can think of as the space-time distance between them. Really, if we're using natural units, it's just that. If we're not using natural units where the speed of light is 1, we can say that CD tau is the space-time distance along the world line. I like to use natural units. But anyway, the role of distance along the world line of a particle is played by the proper time. By the proper time read by the particle's clock. So here's this really fundamental postulate here. Of all the world lines joining two events in space-time, the one actually followed by a free particle is the one for which the elapsed proper time is an extremum, usually a maximum. Because remember, an extremum can be either a maximum, a minimum, or an inflection point. And usually it turns out it's a maximum. Of all the world lines, so this is a postulate we're making here. This is something we're asserting about the universe that experiments would have to show whether or not it's true, and they say it's true. Of all the world lines joining two events in space-time, of all the ways you could get from one to the other, the one actually followed by a free particle no force is acting on it is what we mean by that it's free. It just does what it wants. By a free particle is the one for which the elapsed time is an extremum. The elapsed, I should say, the elapsed proper time, I should emphasize. The elapsed proper time, the time carried by the particle's clock, is an extremum compared to every other possible path, usually a maximum. It's almost always true that the path that the particle actually follows maximizes the proper time, and that's certainly true in flat space-time. And we know this from the twin paradox. Okay, any questions at this point? Right? So in other words, what I want you to imagine is, good thing I brought a spare. What I want you to imagine is, okay, here's two events in space-time, all right? And here is a possible world line joining them. Here's another one. Here is yet another one. I can imagine all these different world lines that a particle could follow, and it can't go faster than the speed of light. That's, of course, a constraint on the motion of the particle. But and I'm kind of implicitly imagining I'm using natural units where c, the speed of light, is equal to 1 here. So in natural units, what would the path of a photon look like? What's a photon world line look like in natural units? So if I have x, t, c equals 1, what if I had a photon traveling through the origin? It's a straight line, and what angle does it make with the axes? 45 degrees, right? Because if the speed of light is 1, then delta x over delta t is the speed of light, which is 1 in those units. So I'm using units where the speed of light c is equal to 1 when I draw these world lines. So a particle's world line can never slope past 1. It can never be something like this. No way, because it would be moving faster than the speed of light if the world line were steeper than this, or actually in a sense flatter than this. So the tangent line to the world line, 1 over its slope, is the particle's speed in these diagrams. So here's a bunch of particle world lines that might connect those two events. In flat space-time, we know how free particles move. How does a free particle move in flat space-time? If there's no force on it, why, it's very Newtonian. It moves in a at straight line at constant speed. We know that, right? And so in flat space-time, geodesic motion corresponds to straight line motion at constant speed. In flat space-time, geodesic motion corresponds to straight line motion at constant speed. Why, of course it does. Corresponds to straight line motion at constant speed. In that case, then the particle stays in a single inertial frame. And I always have to be careful. I mean, a particle is in every frame. So when we say a particle's in a frame, we're being a little sloppy. What we mean is that it's at rest in that frame. When we say a particle's in a frame, it's really in every frame. But the particle stays in a single inertial frame. It keeps the same rest frame the whole time. In a single inertial rest frame, in between experiencing both events. It just drifts between the two events, or as seen by the particle, right, the two locations that in another frame see the particle traveling between them, according to the particle, well, it's just sitting there and everything's happening in its location, is what it comes down to. So, in between experiencing both events happen at the particle's location. In other words, the particle frame in making its straight line at constant speed motion, in its own frame, what's it doing? It's just sitting there at rest at the origin in its own frame. So, in other words, the particle frame is the inertial frame in which both events occur at the origin. Particle frame is the one in which both events occur at the origin. So let's think about the twin paradox here. Okay? So let's look at Fred's stay on Earth frame. Okay, let's say Sally launches at time 0 from Earth, and let's say Earth is at the origin of the frame. So if I want to draw a point here to represent the event of Sally being launched, where should I draw Sally being launched, the event of Sally's launch? At the origin, right? Sally launches. And now let's have her make a round trip. She flies off into space, doesn't even have to be at constant speed like we always do to keep it simple, and therefore crush Sally into smithereens, except she has magic inertial dampers in her ship that keep that from happening. Right? You could never instantly start going near the speed of light. Your body would just go right in that situation. So don't do that. Okay? Sally comes back at some later time. So could this be Sally getting back to Earth in Earth's frame? No. Could this? What does Earth's world line look like? What is the world line of Earth in Earth's frame? So Sally launches from Earth. In Earth's frame, what is Earth's world line? It's just the time axis, right? It's just the time axis. So up here could be Sally returns to Earth. Okay. So Fred stays at home the whole time. How do I draw Fred's stay-at-home world line between those two events? It's just that segment of the t-axis here, right? So Fred's world line. Right? So, is or is it not true that Fred's clock reads the proper time between those two events? It is true because Fred's clock is the one that experiences both events while not being accelerated, while just drifting between the two events. So Fred's rest frame, Earth's frame, is the one in which the time interval between those two events is the proper time. Because the proper time is the time is right on a clock that just drifts between the two events. in a straight line at constant speed, or not moving at all as a special case of that. Fred's world line, Fred's clock reads the proper time interval between those events. Between the two events. Okay. Possible Sally world line. Maybe she flies out and comes back along that world line. Maybe she flies along that world line and comes back. Or maybe she does this craziness, right? Which is what you do in the problems, right? Where here's Zorkon. And Sally does that insane, I'm going to fly it almost the speed of light. I drew it actually like it's at the speed of light. Maybe it's 99% the speed of light to Zorkon and 99% the speed of light back from Zorkon. Whatever. So possible Sally world lines. For any trip Sally takes out somewhere returning back to Earth, does her clock read more time when she gets back or less time than Fred's by the time she gets back? Is the traveling twin the one that ages less or the one that ages more? Less, right? The traveling twin ages less because of time dilation. Always ages less because of time dilation. On a round trip, if there is a round trip. So the traveling twin always ages less because of time dilation on a round trip. On a round trip, you need to turn around somewhere, maybe even be continuously doing it for a while. So could you make a round trip and not ever accelerate the whole time? Could you? No, you couldn't, right? Because you got to turn around, right? You can't make a round trip without accelerating because you have to, if you keep going the same direction, you ain't making a round trip. If you fly off in a straight line at constant speed, never change your direction, bye, 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 I'll never see you again. I hated you anyway, goodbye, right? But assuming that Sally and Fred actually want to come see one another again, on a round trip you need to turn around somewhere, so you must experience acceleration. In other words, accelerated motion will always involve a smaller amount of time elapsed than free unaccelerated motion, the drift between the two events in a straight line at constant speed motion. In other words, the path that a free particle would take between those events, the straight line at constant speed path, has a smaller proper time along it than any other path, because every other path is a twin paradox, had to accelerate, had to come back around, had to have less proper time because of time dilation path. So that's why it is true that in our flat space-time, we know it's all consistent with that the free particle maximizes the proper time, because any other particle has to accelerate and experiences time dilation. And so, in other words, if there's no force, you don't accelerate if you're a free particle. This is saying this is essentially saying, oh, Newton's first law holds because of this. This is equivalent to saying no force, no acceleration. So any accelerated path has more elapsed, less elapsed proper time than the path any accelerated, I should say world line, because that's what our paths are called in space-time, than the world line without acceleration, the straight line at constant speed one. And when I've drawn this in Earth's rest frame, I could draw it in any other frame too. Like if there's another frame where here's Earth, it's a frame where Earth is moving, like it's a spaceship frame where Earth is moving, it would still be true that straight line path minimizes the proper time, and any other world line will have a larger proper time between those events compared to the one that just connects them with a straight line motion at constant speed. Because it's all relative, right? In other words, just hop into another frame of reference and you've got Fred flying between two different locations. They're both Earth, but Earth is flying between two different locations in space-time if it's observed in something that isn't its own rest frame. What questions do you have? Because here's the thing. We deduced all of this in flat space-time. What do you think we're going to assert is true in curved space-time in order to figure out how things move when there's no force on them in curved space-time? What do you think we're going to assert happens in curved space-time? Hint. What's the simplest assumption you could make? So in flat space-time, the path that's actually followed maximizes the proper time. There are special cases which are not very realistic where you might not have a maximum, but essentially it's always a maximum in anything you're going to encounter. So in flat space-time, it's always true in flat space-time. Flat space-time, the path a free particle moves on is a geodesic. It maximizes the proper time. What's the simplest thing you could assume about motion of a free particle in curved space-time? That it's the path that does exactly the same thing. It maximizes the proper time. And this is the key. This tells us how photons move in curved space-time. They move along the straightest possible path in the curved space-time, the one that maximizes the proper time, analogously to, if you want to go to the shortest physical distance between two points on the Earth, you follow a geodesic, a great circle. In curved space-time, you do the equivalent. You move along a geodesic, a path which extremizes the proper time. Analogously. So, in GR, it's still true that a free particle moves along a geodesic in the curved space-time. In GR, a free particle, one with no force on it, is gravity a force? No, no. Gravity's curvature of space-time. A free particle. So why do particles appear to curve in curved space-time? They're moving as straight as they can, but the space-time is curved. In GR, a free particle still moves along a geodesic. Along a geodesic world line in the curved space-time. It maximizes the elapsed proper time. It maximizes the elapsed proper time. This motion may appear curved, as seen in a non-inertial frame. Like the rest frame of this room. But in a local inertial frame, how do I make a local inertial frame? A local inertial frame is one that is in free fall. A free fall frame. The world line is locally straight. Okay, so because I don't have a lot of sense, I will get up here and try to do this. All right, so let's see. So if I were to throw this thing, what's the path going to look like to y'all? It's going to be like a portion of a parabola, right? Now, I'm not likely to fully pull this off, but I want you to picture this thought experiment that I'll do, and then you'll imagine I did it perfectly. If I could do it, I go into a free fall frame. How am I going to go into a free fall frame? Whoop, I'll jump. I'll just step off and I'll launch it, okay? So, all right? So, the chalk was following a parabola as far as y'all were concerned. Thank you, Kathleen. Following a parabola as y'all were concerned. But imagine that you attached a coordinate system to me, x, y, z axes, free falling with me, a local inertial frame. How did the piece of chalk move in those coordinates where if this is like the x, y coordinates, they're falling the same way the chalk is. So how'd the chalk move in that frame?
Straight line.
It moved in a straight line. It moved in a straight line. So geodesic motion looks curved in a non-inertial frame of reference, but it's in a straight line in a local inertial frame where we can transform away the effects of gravity over a small region of space and time and recover special relativity. In that local inertial frame, the metric was that of special relativity in those coordinates, but in Earth-based coordinates, it would be the so-called Schwarzschild metric. Okay? Are you kind of seeing the idea here, the picture of what's going on? Okay, that's the basic idea. So now, it's time for the ta-da moment here. Let's write down the metric, the so-called Schwarzschild metric that describes gravity around a non-rotating spherically symmetric body, including a non-rotating black hole, for example. But even just around Earth, which, okay, it's rotating, but not very fast. It would have to be rotating very, very fast and have much stronger gravity for all this to matter a whole lot in Earth's vicinity, although we have launched probes that have shown the effects of general relativity and the fact that Earth is spinning. We've actually measured these things and showed it's all true. So again, reminder, in flat space-time, the metric was ds squared was c squared dt squared minus, let's do it in spherical coordinates again, minus dr squared minus, yep, so I'll put it like this, r d theta squared, because of the way I'm going to write it in when I put it in the Schwarzschild metric, but of course that's r squared d theta squared, minus, what's the other piece? There's, well, we need some more. We need the r, and we need, oh my god, r, r sine theta dv, yeah, r sine theta dv squared. There's the flat space-time metric. The only spherically symmetric static metric, say that 10 times real fast. The only spherically symmetric static metric, meaning it's not time dependent, static metric that satisfies the Einstein equations is the Schwarzschild metric, which has a sad but remarkable story behind it, obtained on a World War I battlefield by Karl Schwarzschild in 1916. And then Karl Schwarzschild died of, I forget, dysentery or typhoid or one of those terrible things that soldiers can pick up. You know, what a loss. How much more he could have contributed. By Karl Schwarzschild in 1916, just 2 months after Einstein published GR. Einstein didn't think he'd be able to write down a solution to his equations. And Schwarzschild said, here. And Einstein's like, holy crap. So, of course, you know, Einstein knew there must be some solution, but he didn't think it would have a nice, neat analytic form like this. So here it is. It's ds squared is equal to, so just to be consistent, this is going to be c dt squared over there, of course, same thing. It's c dt times the square root of the quantity 1 minus 2 big GM over c squared r squared. So the time piece gets multiplied by that square root right there. The space piece gets divided by it. dr over that same square root. dr over 1 minus 2gm over c squared r squared. And the theta and phi pieces look exactly the same. Minus r d theta squared minus r sine theta d phi squared. All those crazy things you've heard about black holes, time dilation as you approach the event horizon, all that stuff is built into this being the metric around a spherically symmetric gravitating body that isn't spinning. It only applies outside the body not within it if it has a surface and interior. So in other words, this does not apply inside the Earth, but it applies outside it. Well, it doesn't because Earth is spinning, but it's very close to this. There are small corrections because of the fact that Earth is spinning. If you've got a spinning body, including a black hole, you need what's called the Kerr metric, which is more complicated, but we can get a huge amount of mileage out of the Schwarzschild metric. Most of those fun things you've learned about come from the Schwarzschild metric. M is, of course, the mass producing the gravitational field. So, of course, like, what the heck does this mean, right? How do we interpret this? Well, that's what we'll start talking about now. So first of all, as r goes to infinity, and m is by, it's sitting at the origin, obviously, too, I would imagine you'd realize here. As r goes to infinity, infinity, yes, thank you, yes, yeah, 0, boy, now that's too much fun. But to infinity, as r goes to infinity, square root of 1 minus 2 gm over c squared r goes to what? 1, right? Because if r goes to infinity, then 2 gm over c squared r goes to 0 because you're dividing by a bigger and bigger number, goes to 1. So the metric approaches what? How does this compare? If the square root became 1, how does this compare to the flat space-time metric?
The same.
It's the same. So it approaches the flat space-time metric, approaches the SR flat space-time metric. As we'd expect. In other words, if you're far away, well, gravity should not be having any significant effect if you're very far away. So you would certainly expect that to happen. But what is this R beast? R is not simply distance from the center. The radial coordinate R is not distance from the center. So we're going to do a common kind of trick, if you will, maybe not the right word, but we often, when we're trying to explore implications of the Schwarzschild metric, we're going to set dt equals d theta equals d phi equals 0. We're going to consider two events which only differ in their r coordinates, not in t, theta, or phi. Two events that only differ in their r coordinates. So, if that's true, will ds squared be positive, negative, or 0? If d phi is 0, d theta is 0, and dt is 0, will ds squared be positive, negative, or 0? Negative, because you've only got this piece left. So ds squared is equal to minus dr over square root of 1 minus 2gm over c squared r squared is less than 0, less than 0, and then remember, it's just like special relativity, so now you got to think back. If ds squared was greater than 0, then that over c represented the proper time between two events. But if ds squared was less than 0, then ds squared, then the square root of minus ds squared represented the proper what between the two events? What's that? Length or distance. Yeah, it's the proper distance between the two events. So square root of minus ds squared, which here would be dr over square root of 1 minus 2gm over c squared r, is the proper distance between the two events. It's the proper distance between those two events. So compare that to dr. Is dr divided by the square root of 1 minus 2gm over c squared r, is that bigger than dr or smaller than dr? I'm dividing by something which is it smaller than 1 or bigger than 1 that I'm dividing by? Smaller than 1. So I'm dividing by something smaller than 1. So the proper distance, is it bigger than dr or less than dr? It's bigger than dr. The proper distance is thus larger than dr And I'll begin setting up the idea now, and then we'll say more about it next time. If I can log in correctly, which I cannot. Let's see. Okay, because I'm going to show you a picture that you've surely seen before, and I'm going to say it's accurate. There's a reason they draw these pictures like this. So bear with me here while I get this fired up. It'll be our last thingy here. Got to turn the camera towards the screen. This is cool. This is cool stuff. We're going to exceed our vision right now. And everything will be blue. Okay. Gimme, gimme. Here we go. Okay, wake up. Do it. All right. You've seen these like funnel diagrams for black holes, right? Okay. So this is a slice, if you will, through the equatorial plane of the black hole. And so the idea would be, if you could imagine going off in a direction perpendicular to our 3 dimensions of space. It has to be a direction that's not in our space. Take the equatorial plane and curve it down in that direction, which isn't part of our space. This surface right here accurately represents the Schwarzschild metric in the equatorial plane, or for that matter, any plane passing through the center of the black hole. And the idea here is, look at these circles, okay? All of these circles, what the radial coordinate actually represents is the circumference divided by 2 pi. In other words, an ant walks around the circle and measures the circumference of the circle, divide that by 2 pi, that's what r represents. And at first you might say, but that's also just the distance from the center. And that would be true on the blackboard, but not on this funnel. So here's 2 circles with different values of r, right? So I could take this circumference divided by 2 pi, that's a value of r. I could take this circumference divided by 2 pi, that's another value of r, all right? Now, consider what that ds there represents, the proper distance. It's this distance between the 2 circles along the surface. Along the surface. That's larger than the difference in their circumferences divided by 2 pi. That's larger than the change in r, which is the change in circumference divided by 2 pi. Here's like a side view of it, right? So here's a slice through that curved surface, all right? And so for the black hole, if you will, the sheet's going down forever and ever and ever, right? So the center is kind of infinitely far away, if you will. If you think of it going all the way down to infinity, you never get to the center of this surface, the center of the origin there. It's way down at infinity, so to speak. But for any given circles on the sheet, so here's a circle in this plane, here's a circle in this plane, r is the circumference divided by 2 pi, which would be the distance from this axis here, which isn't part of the surface. The axis of the funnel is not part of the surface. It's not a distance you can measure if you're an ant living on that surface, because it doesn't exist in your space. But what you can do is walk around the circle and measure its circumference and divide that by 2 pi, and that would be the distance from this axis, which isn't part of your space. Do you see what I'm saying there, right? So the change in r between these 2 points right here is this distance, right there, but the proper distance, which they're calling d sigma here, would be this distance right here, which is bigger than dr, and that's what's being captured in that. That's what's being captured in that. That metric right there, if I go into the equatorial plane, is describing this funnel. Is describing that funnel. If you set phi equals, doesn't matter what you do with, well, yeah, if you set theta equals 0 so that you're in the equatorial plane in the metric there, then that R piece there really does describe, the R and the theta piece, R and the phi pieces describe that funnel. That is that funnel being described there spatially. All right, we'll talk more about it next time. So now to do all this in 3 dimensions, all you have to do, quote unquote, is imagine a direction which is perpendicular to every direction in our space and stretch everything along that direction which is perpendicular to every direction in our space and do it in 3 dimensions instead of 2. There, that's going 2 into a 3rd dimension. Now just go from 3 dimensions into a 4th dimension and let me know if you can visualize it, because I sure as hell can do the math, but I can't visualize that in 4 dimensions, right? But that's what it represents.